Using your sample from last week that you made, you're now going to analyze it to see if it is indeed a coordination compound, what the coordination compound looks like, doing the following procedures. So this is what we did last week. We finished up to the end of the synthesis, and so this week we will pick up in the analysis section. And so what I'm going to do is just go through each section of this and just talk about what you would do for each part of it. So the first thing, I'm just zooming in on the first part, which is the elemental analysis. So basically it says that what we need to do is to figure out what elements and in what percentages they are present in the compound, but that's expensive and we can't really do that. So what they've done is they've given you some data in order to calculate or in order to figure out the empirical formula. So if you are not remembering how to figure out the empirical formula from the percent composition, I will link a video showing you how to do that up here. But what you'll want to do is go through and figure out basically what you're supposed to do then is figure out how many coppers are there, how many sulfurs are there, how many nitrogens are there, how many hydrogens are there. Okay, I should have started with something other than X. And how many oxygens. So what are all of these numbers based on these percentages? Once you've got the empirical formula, it says assume the empirical formula and the molecular formula are identical, which means whatever these subscripts are, that is your molecular formula as well. And so then you should also figure out the molar weight of the compound. Okay, so that's part A. Part B, it says that we should figure out the percent yield. Before you do anything else, by the way, I forgot to mention this at the beginning, you should weigh out your final sample from last week because you will be using it for some various experiments. So you want to have the mass of how much you actually created before you get any farther. Okay, so then for your starting amount, you'll have your starting amount from last time, how much of this hydrate that you started with. In my video example, I started with 3.49 grams of the copper sulfate pentahydrate. And so you want to convert that to moles using the molar mass, right? Use the molar mass of the whole pentahydrate thing. And then so that would be the moles of the hydrate. Convert that to moles of the coordination compound. And they are a 1-to-1 ratio. I think when you look at your empirical formula that you figured out in the previous one, you'll see that there's only one copper making one copper, like one copper in each molecule, one copper atom. So it has to be a 1-to-1 ratio. So however many moles you started with is how many moles you should end up with. And then you can convert that to grams of coordination compound using the molar mass that you figured out on the previous part A. So molar mass. Okay, so that would be your theoretical yield. And then percent yield is actual over theoretical. Times 100. Okay, so it says use the empirical formula determined above and the mass of copper sulfate pentahydrate as a limiting reagent to calculate the theoretical yield. So that's this. Weigh the synthesized compound in the beaker and subtract the beaker weight, which you also should have from last time, and determine the percent yield. Be sure the compound is completely dry. This may take a week and require grinding to accelerate the drying process. A week in a desiccator is good, so you don't have to worry about grinding it and just weigh it and assume it's dry. All right, so that's part B. Part C, it says conductivity studies will not be directly made, but if such a determination were attempted, a total of 2 ions per molecule of compound would be observed. So what that's telling you is that your coordination compound just has one, I don't know what I want to call it, counter ion. So let me just give you some examples, like NaCl would be something that would make 2 ions, but CaCl2 would make 3 ions, right, when it's separated. And so what this is basically telling you is that you have a ion, the coordination compound, the actual ion part of it, and then one counter ion, and they have the same charge. That's what it's telling you. So we can use that information as we go. All right, part D, hydration analysis also will not be done by individual students, but each student will use the following information obtained by a researcher for measuring the amount of water. So it says the researcher weighed 1.0022 grams of dried compound and blah, 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 heated it for 3 hours and removed it from the oven and cooled it and reweighed it. So that would just remove any water. And they had 0.9274. This is like water that's actually chemically attached that we've heated enough to remove it. So we can figure out the waters of hydration using this. Okay, so mass of water lost, I'll subtract to get that. Molar mass of H2O, I know that. And then this is divided by, it looks a little bit hard to see, but it's divided by the mass of the sample before I heated it. So that's the 1.0022. And then this is the molar weight of the compound that I determined in A. And so I'll figure that out, and that will give me the waters of hydration. So what that's telling me is in my copper compound, my coordination compound, how many waters there are. Okay, so that will give me that information. Okay, so now we're getting to the actual experiments. So now it says weigh out approximately 0.1 grams of my compound into a 10 milliliter beaker, add 5 milliliters of water to dissolve it, and then pipette in 1 milliliter of barium 2 plus ions with a micropipette. Note if any precipitate forms and note the color of the precipitate. Okay, so let me this is from page 13. It's labeled at the lab, the second page of the lab. Let me just pull out a little section here, and it says precipitation studies can be used to determine what counter ions are present in the compound. In this compound, only the sulfate ion can be present. Barium ions react with free sulfate ions in solution to exceed the KSP of barium sulfate and form a white precipitate. So if the SO4 2- is functioning as a ligand, no precipitation will occur. So what that means is if you see a precipitate, that means SO4 is functioning as a counter ion. It's not part of the coordination compound. It says white precipitate. I mean, your solution will be super purple, so it might look purple, but it's like white in a purple solution. Anyway, it would be a white precipitate. If no precipitate forms, meaning if it's totally clear and you can still see through your solution, then any sulfate ions are ligands inside the brackets. That's what we're trying to determine. Where does SO4 go? Outside the brackets or inside the brackets? Okay, so that's what this part of it will tell us. And then the last section is the verification of the number of NH3 ligands. It says obtain 1 10 milliliter volumetric flask and 8 to 10 milliliter beaker, 8 10 milliliter beakers from the stock bench, weigh accurately enough compound to make 10 milliliters of 0.1 molar. Okay, 0.100. Remember that means moles per 1 liter of compound. How are you going to weigh that? You're going to need to convert it to grams. So you can use the molar mass. Again, you figured this out in step A. And of course, that would be how many grams you'd want in a whole liter. You don't want a whole liter. You want 10 milliliters, right? So convert that to liters. So that would tell you how many grams to weigh out. Okay, so put that many grams in a volumetric flask, fill it to the line with water, then put 1 milliliter of each solution in the 10 milliliter beakers. Okay, so 1 milliliter in all of your little beakers. By the way, depending on how your pipette is labeled, it might be in microliters, which is 1,000 microliters per liter. So just make sure you're adding enough solution. It needs to be either 1,000 microliters or 1 milliliter. Okay, so you do that, and then it says label the beakers 0 through 7, and then add 0 to 7 milliliters of 0.1 molar HCl, so hydrochloric acid. So this is 1 milliliter of your stuff. In the first one, you'll add 0 milliliters of HCl, 1 milliliter of HCl, 2 milliliters, you get the idea. Okay, so you'll do that for all of your beakers. Using a micropipette, notice the color changes that occur as the HCl is added to each beaker. Using glass stirring rod is fine. From your observations, determine the number of NH3 ligands. This value should be recorded at the point when the solutions have become essentially colorless. So you're looking for a colorless solution due to the low intensity of the copper aqua complex ions. So again, going back to that page 13 of the lab, let me erase this stuff. NH3. When NH3 is exposed to acid, it is converted to the polyatomic cation NH4+, which has used its lone pair of electrons in the attachment and is no longer capable of ligand formation. As the NH3 ligand is converted to NH4+, a shift in color and intensity of the compound to the original color occurs. The number of acid equivalents, okay, so the number of acid equivalents, how many milliliters, meaning, necessary to observe the color change is used to determine the number of amine groups. So again, we're looking at, this is the thing, and then we're looking at NH3 in here, and then we're trying to figure out this number, and this number should be how many milliliters of HCl it took to make it colorless. So if it took 4 milliliters, then this would be a 4. If it took 5, this would be a 5. If it took 2, this would be a 2, right? So that's what we're trying to figure out in step F. Once you have all of that information, then you can write up your lab report, and you should make sure you address all of the questions it asks you for here. But what you'll find is that you've done a lot of this already, right? So it says elemental analysis, provide calculations for the empirical and molecular formula, and calculate the molar weight. Okay, we already did that like back in step A. So however you want to organize it is fine. Just make sure everything in here is addressed. And the most important one is, what is the structural formula of this compound and why? So go back, look at what your empirical formula was, right? However many of each of these things you had, but write it like this, right? So how many NH3s do you have? And how many H2Os do you have? And sulfate, where does that go? Inside or outside? And how many of those do you have? And what it should add up to is you should have the correct number of everything that you found for your empirical formula. So if you put that there should be 2 nitrogens, and then down here you say 3 nitrogens, you would want to comment on that and say, like, this isn't supported by what my empirical formula looked like, this is my data showed, I don't know, however you want to address it, but they should match up. If you had 5 sulfurs in here, then you should have 5 sulfurs down here, etc. Okay, so that's the end goal, is to figure out, what does it actually look like? What are the ligands? What are the counter ions, etc. Okay, and that's it. You're done with the lab.